This is our first look at a function that has multiple transformative operations going on in it. So, how do we know what to do first? That's where the order of operations comes into play. The fact of the matter is that each transformation is caused by the presence of a new operation beyond the basic operation. In this case, the square root is the basic operation, which means we have other operations in addition to that. We have a multiplication by -1, a subtraction of 3, and an addition of 5. But those operations, each of them causes a different transformation, but they also have to happen in a particular order. The entire reason we have order of operations is so that we have a standard way to make sure that everybody's getting the same result when they're looking at the same problem. So, if we want to know what the transformations are, we also need to talk about what order they occur in. So, one thing that may help, just as a little technique we can do here, is to just pick an input value. Any input value doesn't really matter. We should probably make sure, because of the square root, that whatever we pick we're actually going to be able to get an output for. So I'm going to suggest that we take f of 7. Now, the reason why I'm doing this is because it will allow us to see which operations occur and in which order, because we're actually going to do them. Whatever we do first, by the order of operations, that's the operation that occurs first. So, the first thing we need to do here is the subtraction. 7 minus 3. That's our first operation, which means that is the first transformation that occurs. Whatever this subtraction of 3 does, that is the first transformation. We'll come back to talking about what exactly it does in a moment. Let's finish with this. Let's finish going through it and talk about the different operations and when they occur. So the next thing we would do here is the actual square root. Now that does not cause a transformation because it is the basic operation. It's the operation that makes this function what it is. You know, a parabola versus a line versus whatever the names are of the other graphs. It's that square root operation that makes this the graph that goes like that. So it doesn't enact a transformation because it's the basic operation. It's the characteristic operation of the function. But the linear operations, when we get to one, will cause the transformations. So our next step is to do that square root of 4, as we said. And the square root of 4 is 2. Now the next step, if the entire goal was simply to evaluate this, we'd probably just call that -2 and not think of it as its own step. But I'm going to really kind of emphasize it here because we really need to be aware of the operations that are occurring because they're causing the transformations. So this multiplication by -1, that is the next linear operation, the next transformative operation. So this out here, and if I may, I'm going to actually write in the 1, as I've been doing. This multiplication by -1, that is the second transformative operation that occurs. Well, at this point, it tends to be fairly obvious because there's only one thing left, the addition of 5. So, this addition of 5 is what happens third. Now, it's not necessary to do this every time. I would hope that at some point, if not already, that you can track through the order of operations without actually having to perform them, but it's a great way to make sure. If you can evaluate a function by performing the operations in order, then you know what order they happen in, and you know what order the transformations will occur in. That's the only purpose of doing this, was to put the order to the transformations. So I'm going to get rid of that. We don't need it anymore. Now that we know which operation occurs first, second, third, we can start talking about what effect they have. This is an addition, or subtraction in this case, which means it is a shift. But part of that is we have to talk about, does it occur before or after the basic operation? Well, as we saw, we did that subtraction of 3 before we did the square root. So this happens before the basic operation. You might think of it as happening inside of the basic operation. And that makes it a horizontal transformation. So the first should be a horizontal shift. Horizontal because it occurs inside or before the basic operation, and a shift because it is an addition or subtraction of a constant. Now, part of talking about a shift is we need to say how far in which direction. We did say that it is horizontal, but there's 2 horizontal directions to go, left and right. And we should probably say something about how far to the left or right we go. Now, in this case, it's simple enough that if you do what I suggested not to do, and go, oh look, it's -3, that must be, and the horizontal one goes backwards, so that must mean it goes +3 to the right, you'd get away with it. If I might suggest, here's the best way to do it. The way that we find the actual amount of the shift is, remember, by choosing a y value and then solving. Now, we don't need to worry about undoing these operations because they're not what caused the horizontal shift. We don't need to worry about undoing the square root because that's the basic operation. What we really need to do is know what operation undoes a subtraction of 3. And here's an interesting way to do that. You take that inside expression and set it equal to anything, really, but 0 is the best one. 0 is the best value to use. And then you solve for x. Why is 0 the best value to use? Because the solution to this equation then is the amount of the horizontal shift. 0 is unique among numbers like that. Whatever we add to 0, that's the number we get. So if we take that inside expression and set it equal to 0 and solve, that is the amount and direction, because it is positive, the amount and direction of the horizontal shift. Excellent. Now, next up is this. We have a multiplication by -1. A multiplication by -1 causes a reflection. But is it a horizontal reflection or is it a vertical reflection? Well, again, that comes down to when does the operation occur? If it occurs, like the subtraction of 3, if it occurs before we get to the basic operation, then it's horizontal. But when we evaluated f of 7 before, we did the subtraction of 3, then we did the square root, which meant this came afterward. Since it happens after the basic square root operation, it is a vertical transformation. Now, unlike the shift, we don't have to say anything more than that. reflections are just reflections. We don't have to say how far or which direction because the distance of a point from the axis is going to be the same, just on the other side of it. So vertical reflection is good enough. Well, that leaves us with one last operation, the plus 5. Well, again, by the time you get to the end of stuff, things tend to be a bit more obvious to work with. Like, well, first of all, we already know that this happened after the square root. And if this happens after the multiplication by -1, then it also happens after the square root. That makes it a vertical transformation. Now, beyond that, the type is addition. That is a shift. Now, once again, vertical tends to be much easier than horizontal. With horizontal shift, we had to do something funky like that. With vertical shifts, with any vertical transformation, what it says is what you do. So if that says add 5, then we're going to go up 5. And that's simple. Okay, but here's the interesting part. How do we actually produce the graph of f of x then? See, it's very easy if you're only doing one single transformation, like say shifting to the right 3, to just pick up every point and go right 3 spaces. That's pretty easy to do. But that's not where we stop. After moving to the right 3, we then need to reflect vertically. And then after reflecting vertically, we have to shift up 5. That means we need to produce the graph after this happens, then take that graph and produce what happens after the vertical reflection. And then take that graph and see what happens with the vertical shift. That's a lot of graphing for one problem. We take the original basic function and then make a new graph for each transformation that occurs. That's kind of a really unwieldy way to do it. However, we did see in the previous videos how these things actually played out with some of the ordered pairs. So I'm going to make a suggestion. Let's not transform the graph. Let's transform some ordered pairs. We know what effect each of these things will have. A horizontal shift to the right 3 means that our x values need to be 3 bigger than they were in the original. So to make this happen, we literally are going to take all of the x coordinates and add 3. We're going to take every x coordinate of the original graph and add 3 to it. The vertical reflection produced a y value and then multiplied it by -1 to change its sign. So let's take our y coordinates and multiply them by -1. A vertical shift up 5. In a vertical shift, we produce the y value and then add the 5. So let's take the y value and add 5. Now, it's important, remember these things have to happen in a certain order. So every y value has to be multiplied by -1 before we add the 5 to it. Now, let's do this by taking some known ordered pairs from the original basic square root function. good idea to take at least 4 ordered pairs when you do this. Some functions may require more than that, but 4 I think is good enough for the square root function. 0, 0. Now again, these ordered pairs are all coming from the library of basic functions, our knowledge of this function already, but even then, it's not that hard to come up with a few things. Just pick x values that are nice for doing a square root, like the square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. That's probably far enough, because if we go further, we're going to get x equals 16, and as we saw in the previous video, that takes us kind of far off to the side of the graph. So let's try to avoid x and y coordinates that go too large. Now, we have to do 3 things to this. We have to enact the horizontal shift to the right 3, and what we said is we can do that by taking every x coordinate and adding 3. So this x coordinate of 0 becomes an x coordinate of 3. Note that the y coordinate has been unaffected. This x coordinate gets 3 added to it and becomes a new x coordinate of 4. The y coordinate is still 1. This x coordinate of 4 gets shifted to the right 3. We add 3 to it, and it becomes 7. The y coordinate of 2 is unaffected. And this x coordinate again, the y value of 3 is unaffected. Literally, add 3 to each x coordinate. The second transformation was the vertical reflection. We said that that occurs by taking the y value and multiplying it by -1. This time, we're going to leave the x coordinate alone and take the y value. Well, here, we're taking the 0. And 0 times -1 is still 0. So, no change there. That, again, that's a point that is already on the axis. So, like we said about reflections and mirrors, if you are touching the mirror, your reflection is also touching the mirror. There's no distance between them. So, in the next one, we're 1 space above the x-axis. We multiply that by -1, and we end up 1 space below the x-axis. Again, the x-coordinate is unaffected by this. We take the y-coordinate here. Instead of being 2 spaces above the x-axis, we end up 2 spaces below it. The x value is unaffected. And lastly, no change in the x value. The y value is now the opposite sign. We have one last operation then, the addition of 5, which we classified as a vertical shift, up 5. So, we're going to take our y coordinates and add 5 to each of them. The y coordinate of 0, when we add 5 to it, becomes a y coordinate of 5. The x coordinate is unaffected by this. Here we take the y coordinate -1, and when we add 5, it becomes +4. Our y coordinate of -2, when we add 5, becomes a y coordinate of +3. And lastly, a y coordinate of -3, when we add 5, becomes a y coordinate of +2. These, then, are the corresponding points on this transformed function. These are the points on the original function, and these down at the end are the corresponding points on the transformed function. Let's take a look at the graph. Now, one of the benefits of this is I can see what portion of the graph I'm going to need now. I have entirely positive x values and entirely positive y values. We know that from the domain and range of the square root of x. And on this, I seem to still have entirely positive x values. Well, my y values are counting downward, but I didn't go far enough to get into the negatives. So every one of these points seems to be positive x and positive y. I can also see how far out I need to go on the axis. So that helps me get an idea of how I'm going to set this up. So I'm going to start by marking the original function, 0, 0, 1, 1, 4, 2, 9, 3. Now, the new function is at these points. So I'll start with the corresponding point to 0, 0. Now 0, 0 is highly recognizable in this because it's the end point. Literally, the graph just stops dead there. Or if we think of it as going left to right, we can think of it as the starting point. But in any case, there's nothing to the left of this. Well, what we're going to see when we graph this is that 3, 5 is going to be the end point, the starting point, if you will, of the transformation function. So after 3, 5, we have 4, 4, 7, 3, 12, 2. Now, not obvious perhaps, but we can see the different elements of it if we look closely. We said there was a horizontal shift to the right. Well, certainly, they're both have an endpoint on the left and extend to the right, but the red graph is further to the right to start. It starts at x equals 3, whereas the original started at x equals 0. We said there's a vertical reflection. Well, certainly instead of arcing upward from its starting point, this one arcs downward from its starting point. So there's our vertical reflection. And a vertical shift up 5. Well, certainly this graph is higher up, at least to start, than the original function. Now, it does dip lower, of course, because remember the vertical reflection. But the point is that it does start 3 to the right, 5 up, and it is arcing upside down compared to the original. This method of producing the transformed ordered pairs is infinitely preferable to having to draw a graph and then draw a second graph and then a third and then a fourth and so on. And let's face it, this has only got 3 transformations in it. It's possible that there could be more. We have a whole family of transformations we haven't even talked about. We didn't even include all the types in this. There could have been a horizontal reflection, but I did not include it. So imagine for every additional transformation there is, having to produce another graph and then another graph. It gets really disgusting. This method is, I think, easier to work with. Certainly it takes up less space on your page and involves less graphing. I mean, it takes time to draw these grids out. Think about, how long it takes to sit here watching me draw them out in the middle of a video as opposed to just kind of having it ready to go. Now imagine you have to draw it out every time. And think about this. On the test, if I give you a grid to draw on, you only get one grid. Where are you going to draw the other graphs that lead up to it, So this method of classifying these and performing the operations on the ordered pairs is, I think, way preferable than trying to actually come up with all this by hand. Now, if there's only one or two transformations and they're simple enough, it might be easy to go kind of directly to the graph. And the more familiar with this you get, the easier it will be to do this. I'm well enough practiced at this. I can just go to this graph. I can do all of these things without having to write them all out. But you guys are new with this. You should write this all out. So as we did, we identified the order of the operations. We classified each one as what type of transformation with all relevant information. In the case of a shift, we needed to say which direction, left or right, up or down, and how far. Then we figured out what effect it had on the ordered pairs and made it happen, thereby allowing us to produce the graph.